Today, we're diving into an exciting topic: vector databases, a game changer in modern data science. These powerful databases store and manage data as vectors, making them essential for cutting-edge tasks in machine learning and artificial intelligence. We will discuss how vector databases fuel innovation in recommendation systems, natural language processing, and so much more. Let's jump in and explore this fascinating world together. Vector databases are specialized systems designed to store and search high-dimensional vector data. These databases are at the heart of cutting-edge applications like recommendation systems and natural language processing. Unlike traditional databases, vector databases are built to handle embeddings, numerical representations of unstructured data in vector form. This specialization enables lightning-fast vector searches and efficient data handling. Key use cases: semantic search, personalization, and AI-driven analytics. Pinecone, Weaviate, and FAISS are some popular vector databases. These platforms are masters at handling the complexity of high-dimensional data, making them must-haves for powering today's data-driven innovations. Vector databases are purpose-built for managing high-dimensional vectors, which represent data in continuous vector spaces. Think of this as a unique approach to storing and navigating data, enabling efficient similarity-based searches. Here's a simple way to imagine how it works. Let's say we create embeddings, vectorized representations of two dogs by analyzing their pixel patterns. These embeddings are stored as vectors in the database. If the database recognizes these vectors as closed based on their similarity, it indexes them accordingly. Now visualize this in a simplified high-dimensional space, in this case 2D. Suppose we create embeddings for dogs, cats, men, and women using two features. Feature 2 might be the number of legs, where dogs score higher than humans. Feature 1 could be the ability to recognize objects, where humans outperform dogs. Plotted on these two scales, humans cluster together on one side, while dogs are further away. In practice, we use hundreds of features, enabling more precise clustering of similar objects, making this approach incredibly powerful. This concept underpins the ability of vector databases to organize and search data effectively, whether it's recognizing animals, finding similar images, or clustering complex datasets in applications like natural language processing and recommendation systems. The result? Better, smarter, and faster insights. Any object can be converted to an embedding: pictures of dogs, humans, documents, sound files, and more. The idea is that vectorized two documents or pictures with similar feature values will be clustered together, making them easy to find. Why use vector databases? Let's suppose we store a document in a traditional SQL database. We will store the document and its metadata that makes it easy to find the document. But if the query is about finding two documents that are similar, that can be quite difficult with a traditional database. Instead, let's assume that we vectorize the documents and place them in a vector database. Now similar documents will be closer, so we can find similar documents faster. But if the query is to find the number of words in the document, traditional database might be more appropriate. So that's the point. Vector databases make finding similar items quite fast, something we need in modern AI-dominated world. Next, we will go over the implementation of a vector database Pinecone to make LLM queries provide better answers. In a vector space, the distances between vectors reveal relationships. The closer the vectors, the more similar the data they represent. This is the foundation of how similarity metrics work, such as cosine similarity, measures the angle between two vectors, focusing on direction rather than magnitude, ideal for text or document comparison. Euclidean distance calculates the straight-line distance between vectors, commonly used in geometric or spatial contexts. Dot product captures the magnitude of similarity between two vectors, often applied in recommendation systems. These metrics help us quantify how close or similar data points are, enabling efficient and accurate vector-based searches. Next, we'll dive into a practical example to see how to find and interpret similarity in action. Let us take this example. We have 4 documents and we create vector embeddings of the documents. The vector size will be the total words in all documents, in this case 7 words, so each document is represented by a vector. If the corresponding word is in the document, we place a 1, otherwise 0. Next, we find the dot product matrix, where we find the dot product of pairs of vectors. We ignore the dot product of a vector by itself, as they are similar anyway. Remember, dot product is taken by multiplying corresponding elements in the vectors and adding them up. For example, if you multiply S1 and S2 vectors element-wise, we find 1 times plus 1 times 1, and that is 2. So S1, S2 entry is 2. Similarly, we find other entries of the dot product matrix. Now, looking at the matrix, clearly S1 and S2 are similar, but S1 and S3 or S1 and S4 have no similarity. This makes it easier to find similar clusters of documents. In this case, we would cluster S1 and S2 in one cluster and S3 and S4 in another cluster. By inspecting the documents, you can easily see why. S1 and S2 share similar words, and S3 and S4 share their own similar words. S1 and S2 are about fruits, and S3 and S4 are about tech. So we can apply this concept to any vectors to find similar clusters. Now let's look at how databases work. At the heart of vector databases lies an essential concept: indexing. Indexing organizes high-dimensional vectors in a way that allows for fast similarity searches, so you can quickly retrieve related items without having to sift through an entire dataset. The magic happens with search algorithms like approximate nearest neighbor, AN. These algorithms don't exhaustively compare every vector. Instead, they approximate the nearest matches within these complex, high-dimensional spaces, dramatically speeding up the process. This powerful combination of efficient indexing and smart search algorithms is what makes vector databases such indispensable tools for modern data retrieval tasks. Whether it's powering recommendation systems, semantic search, or AI-driven analytics, vector databases are designed to deliver results quickly and effectively, even in massive datasets. There are many advantages to using vector databases for modern applications. Fast similarity searches. They excel at quickly retrieving similar items from massive datasets. Scalability for high-dimensional data. They handle high-dimensional datasets efficiently. Flexibility across domains. From recommendation systems to natural language processing, their versatility allows them to be applied across a wide range of industries. Importantly, vector databases can complement traditional databases. While vector databases specialize in similarity-based tasks, traditional databases are better suited for structured queries like counts, joins, or simple lookups. Together, they form a powerful hybrid system that combines the strengths of both, enabling advanced and efficient data management solutions. Vector databases have become critical in the AI-driven era, enabling a wide range of powerful applications, including semantic search. They enhance search engines by understanding the meaning behind queries. Recommendation systems. By comparing user preferences and behaviors through vector embeddings, they help generate personalized recommendations for products, content, or services. Image and video searches allow for content-based searches by analyzing and retrieving visually or contextually similar images and videos. Anomaly detection. In high-dimensional datasets, they identify outliers and unusual patterns efficiently, crucial for fraud detection, cybersecurity, and predictive maintenance. There are many popular vector databases currently available, each catering to different needs and use cases. Some offer free tiers with limited usage, which are great for experimentation or small-scale projects. Examples include Pinecone, Weaviate, and FOSS. These can help you get started without significant investment. Finally, there are challenges in using vector databases. Managing storage, search efficiency, accuracy, speed, as well as hardware needs can be critical. But they are the future. So, understanding how to use them in your project is critical. In the next video, we will see an implementation of a vector database for LLM queries using Pinecone.